Hello and welcome back to the lab. Today we're going to continue working on the HP400D vacuum tube voltmeter. When we left off, we had done a complete recapping of this instrument, which is something I don't normally do, but in this case we had several bad electrolytic capacitors, so we decided to replace all of them. And so we put in these custom manufactured CAN capacitors from Hayseed Hamfest for the high voltage capacitors, and for the low voltage uh, high capacity capacitors, we just use standalone electrolytics on these terminal strips for each one. So all of those electrolytics have been replaced, as well as this one here, which is the one that goes across the meter movement itself for damping. This one actually tested good, but it had some electrolyte leaking out of the positive terminal, so I replaced that one as well. This is something I don't normally do, just randomly replace all the capacitors. I don't really believe you should change parts that aren't defective, but in this case, we had so many bad parts for whatever reason that I decided to change them all. Plugged it in, turned it back on, and it immediately blew the fuse, which was the original symptom. The original symptom still existed. I was really concerned that the power transformer itself had a short internally or something like that, which would have been bad news indeed. Um, But I went through with an ohm meter and checked all the primary and secondary windings of this transformer and compared that to a good transformer from another 400D that I had already repaired, and I knew that was fully functional. And both sets of readings compared very similarly. Um, and didn't measure any shorts to ground or anything like that. So I probably assumed that the transformer was probably okay. So let me show you on the schematic what I did after that. So here we are zoomed in on the power supply section of this instrument, on the power supply section of the schematic of this instrument. Um, I had a feeling that maybe the silicon rectifier here was shorted or something like that, because they had already replaced the selenium rectifier that usually goes here with a silicon bridge rectifier. And so I checked these diodes out and they are not shorted. There's no way for me to measure the voltage because it blows the fuse immediately upon power up. Um, I decided that I should pull the rectifier tube, V6, 6AX5 rectifier tube, and that would prevent any voltage getting through to the high voltage B plus section of the schematic and of the circuit. And that way I would be able to test to see if the 12 volt DC that provides 12 volts DC to these filaments is all working properly. I would be able to measure the voltages on the secondary windings over here, as well as the high voltage secondary windings and the 6.3 volts AC secondary windings for these filaments as well, without having to worry about any of the rest of the circuit pulling down the B plus supply or any other situation. So it was really just a problem isolation. I pulled out V6, turned the unit on, and I noticed, first of all, that it did not blow a fuse. So there's some valuable, helpful information. The fuse did not blow without the rectifier tube in the socket. When I measured the DC out here, which is supposed to be 12 volts DC, it actually measured a little higher than that because we were not drawing the right amount of current from the output of the rectifier, but there was a little more than 12 volts DC here. Okay, we also had the 6.3 volts AC across these filaments. When I measured the high voltage AC on the high voltage secondary winding, we had 420 volts on each side of the secondary reference to the center tap, which is grounded. So I concluded that the power transformer was indeed not defective, but it had to be something on the secondary side of the high voltage winding, because the only thing different was I removed the rectifier tube from the circuit. So something out here had to be shorted or loading down the circuit. But when I measured the DC resistance at this point over here across these capacitors, it was not a low impedance. I don't know, it was many kiloohms, many hundreds of kiloohms. And the same over here at the output of the regulator, it was not shorted to ground. It was many hundreds of kiloohms there as well when I measured with the power off, of course. And these capacitors discharged, although they were already discharged because they'd never been charged. Um, so it means that, what can it be? How could, if there's no shorts in the high voltage supply, but it blows a fuse when I put the rectifier tube in, the only thing I thought that it might be is the rectifier tube itself could be bad, but I can't imagine how the rectifier itself could be bad. But what I did was I took the rectifier tube, the 6AX5, out of my working 400D and plugged it in to this socket and turned it on. Lo and behold, we did have high voltage here. We also had regulated high voltage at the output of the regulator over here. In fact, I believe maybe the entire circuit was working, although I also had the rest of these tubes also pulled out, so there's no way to know if it was actually working. But we did have regulated 250 volts. It actually measured about 262 volts actually, here with no load, with no significant load over here. I concluded that the rectifier tube must have been the defective element. I took another close look at the rectifier tube, and I noticed that it doesn't look the same. Here is the good rectifier tube on my right that is working just fine, that I pulled out of the working 400D. Here is the tube that is in the instrument I'm working on. Very tiny, relatively. Why would that be? It seems like there's only one anode in this rectifier tube, not two anodes, two plates, which are on this rectifier tube. That can't be right. And then look at the part number, 6AX5, 6X5. The guy who sold me this 400D had installed the incorrect rectifier tube in the instrument, and that was blowing the fuse. This is a completely different pinout, and it's not a full bridge, a full wave rectifier. It's only a half wave rectifier, a single diode inside this tube. And there are two diodes inside this tube. So that's what was wrong. That's what was blowing fuses all along. So I placed an order for a new 6AX5, not a new, but a new old stock 6AX5 rectifier. And when that comes in, I'll put it in our voltmeter. But in the meantime, I can use this one that came out of my working 400D. And I will reinstall the rest of the tubes in the instrument and see if maybe the entire instrument is working. Let's do that now. But before I do that, I wanted to make a quick correction. I looked up the 6X5 tube, and it does in fact have two plates, two anodes. They are just far, far skimpier than the ones in the 6AX5 tube. It's hard to see. It's probably very difficult to see on video, but the the plates um, are on each side of the indirectly heated cathode in this manner, so they overlap very slightly, and it makes it look like it's only one plate that surrounds it in a sort of a flattened circle. Um, but that's not what it really is. And the pinout is actually matches the one in the 6AX5, but the design is completely different. This one is actually, according to the literature, is designed for specifically for AM car radio power supplies. So that's the 6X5. I don't know why it was in my instrument. It doesn't belong there, and it was causing the problem. Okay, I've hooked up two voltmeters to my instrument. Um, this one is connected to the plus 250 volt regulated B plus voltage, and this one down here is hooked up to the plus 12.6 volts coming out of that silicon bridge rectifier. Let me focus the camera on my voltmeters to show you what those readings will be, and I'll plug in the 400D and turn it on, and let's see what we get. So the upper voltmeter is connected to the plus 12.6 volts DC, and the lower voltmeter is connected to the plus 250 volts DC. Let me turn the 400D on, and we'll see what the voltages are. Here goes. So you see that the 12.6 volts is actually reading 12.6 volts, it looks like. And it looks like the 250 volts DC is reading 253. Now I do notice on the front panel, I don't have the camera on the 400D, but on the front panel, there is some movement on the meter front panel. I don't know if this instrument is working or not yet, but it looks like we do have our power supplies back, and we certainly are not blowing fuses any longer. The indicator light bulb on the front panel, or the power on indicator light bulb, was burned out, so I replaced it, and now it is fully illuminated when I turn the power on. Okay, so I've removed the meter and removed the front bezel from the meter and cleaned the glass on the back side of the glass. And there was also a little bit of some kind of something on the front of the glass. So I cleaned both sides of the glass and reassembled the meter, reinstalled it back in the instrument, realigned and calibrated the entire instrument. And now I want to just do a quick demonstration of the accuracy of this instrument. We're looking at 1 millivolt at it's at 400 hertz. Oh, it's actually at 4 kilohertz. Here we go. There's 400 hertz. There's 10 millivolts. There's 100 millivolts. Here is 1 volt. There is 10 volts. And there is 100 volts. All of those ranges look really good. We can do the threes as well. Let's do that. Here's 30 volts, 3 volts, 300 millivolts, 30 millivolts, and 3 millivolts. All of those ranges look well within spec. The specification for this instrument is plus or minus 2% for the majority of the frequencies. Towards the lower and upper frequency ranges, that uh, tolerance gets wider. But at the 400 hertz level, um, the frequency tolerance is plus or minus 2%. So all of those ranges read within 2%. So the instrument is in spec. It also passes all the frequency ranges, but I'm not going to demonstrate all of those right now. So let's zoom my camera back out. We have the completed 400D. Now, my plan was to give this instrument away to one of my viewers who would be interested in owning a piece of vintage Hewlett-Packard test equipment. One thing I wanted to let you know is that the leather handle that was on the top of this instrument, I decided to keep that for myself. So if you get this instrument, you won't be getting a leather handle. I'm going to keep that case with the leather handle on it for one of my other 400 series voltmeters. Um, so, so this one will not have the leather handle attached, but it does have the tilt stand at the bottom, of course, binding post for input and output, banana jacks, and a range switch, and the standard meter. And it comes with a built-in power cord. Doesn't need a separate uh, plug-in power cord. It's permanently attached to the instrument on the rear panel. You will notice if you look very closely, I don't know if it even shows up on camera, that one of the previous owners has etched an asset number or something into the front panel. It's very minor, and but it goes through the paint, and therefore it can't be removed. It's going to have to remain a permanent part of this instrument. Um, that's the only thing I think in terms of cosmetics. There is a slight um, some kind of damage here that is just also going to have to remain part of the instrument because I'm not going to repaint the chassis or the case rather. So if you'd be interested in owning this instrument, send me an email to the email address that are in the description of this video, and I'll I'll take a look at all the entries received, and I'll choose one to send this instrument to, and let you know who the winner is. And you can send me your address information and so forth, so that I can get this instrument out to you, and you will be the proud owner of a Hewlett-Packard Model 400D vacuum tube voltmeter. So that'll do it for this video. Thanks very much for watching. Please like and subscribe, and send me an email. Maybe you'll get to own this 400D. Thanks again.